need to calculate this limit. You could also use other guides, right? But you have to approximate it by a sequence of bounded functions, by a Cauchy sequence of bounded functions. Sequence is Cauchy L2 of R.
You can follow the integral to the bottom.
That's right. Thank you. Okay, so that's it. And then, well, to figure all of this out in detail, I will turn you to the problem sheet. Yeah. You need to have done this once, because otherwise you don't know what you're doing. So, the hard work is done. The hard work is done. Now, of course, you must not fall into the trap of thinking that whatever we showed for the dp integration before should automatically be valued still for the unbounded functions. Let me first tell you something that is still true. So properties that still hold. Properties. This is very important, okay? So the first one is that if you take the integral over f, so this is now f unbounded. Unbounded measurable. And given p and p. Integral f dp, if you then take the adjoint, and everything that this is an unbounded operator whose adjoint you take. Do you remember how tricky that was to calculate that? This is the integral over f bar, the complex conjugation of the f dp. Huh? Good. Second, integral alpha f plus g dp. For alpha in the complex numbers and f and g unbounded measurable. If f and g are bounded, f and g bounded, you have equality. F, g bounded, you have equality to alpha times integral f dp plus integral g dp. And you'd say, well, that's a proper integral that is linear in this way. That is C linear, right? However, for fg unbounded, all you know is that the left-hand side is an extension of the right-hand side. Why is it not equal? You remember what the extension is. It means on the smaller domain it coincides, but the domain is bigger. There are domain issues to be taken care of, to be considered. And the domain of the right-hand side, is actually the domain of integral r, absolute value of f plus absolute value of g dp. Third, remember this magnitude f multiplied by g dp, which for fg bounded Barrel functions, this was simply equal to f dp after integral g dp. But again, for unbounded Borel functions fg, this is merely an extension. Not really, this is even an extension. Fg unbounded. Okay? And the domain of the right-hand side is, so the order matters. Domain of the right-hand side is the domain of f intersected with the domain of f times g. Well, I should say the domain of integral f dp, domain of integral f times g dp. Okay? But here, this first one, that is valid in all cases. This remains an equal sign. That is very useful. And the hard work is done. So let me state the inverse spectral theorem, and proof is half a line. So remember in the introduction I said, given a self-adjoint operator A, you can construct the real Borel measure, the complex Borel measure, and finally from that, in the sequence, the projection valued measure. Now in the technical part of today's lecture, I went the other way around. I started with some projection valued measure, constructed the real and the complex valued measure from it, and now I will even go a step further, and I will construct, given a projection valued measure, I will construct from it a self-adjoint operator. It's really exactly the other way around. So that's number 4, the inverse spectral theorem. But this way, you've got to know all the actors in the spectral theorem and all the definitions I made in the beginning, so I don't even need to give the proof next time. You can already use the spectral theorem. Okay? The inverse spectral theorem is given, so that's the change of perspective, yeah? Given a projection valued measure P, we have that we can construct a self-adjoint operator. Well, we can in fact construct many self-adjoint operators. We can construct a self-adjoint operator, let's call it A, but now it's not the P that is the PA because it comes from an A, now we have the A that's constructed from a P. So I call it like this. Given this, we can construct this guy, and we construct it as the integral over the R, but you know what I mean by this actually, the integral of R into the complex numbers here. dp. That's it. Where's the self-adjoint? Proof. Well, I calculate AP star. What is AP star? AP star is in R dp star. Its integral in R complex conjugate dp, all over the real line, of course. What is in R again? In R takes us from R into the complex numbers, lambda goes to lambda. Takes over real number lambda, a complex number lambda, and it's the real complex number. So obviously in R bar at lambda is defined as, well, what else would it be? It's always for the complex conjugate functions. It's the id R of lambda bar. So, but the id R of lambda bar, because lambda is real, is of course id R of lambda. That means id R bar is the same function as id R. So this whole thing is the AP. AP star is AP. This is a self-adjoint operator. So we did exactly the opposite of what we want to do. Next time, and that is actually only wrapping up the stuff the other way around and inverting everything we did, okay? But with the notions we now introduced, next time I don't want to have given a P and get an A. I will ask the question, given the A, is there a unique P from which it comes? The answer is yes, and that's the spectral theorem, okay? But already this is incredibly useful, right? For instance, one could define now for this AP, so outlook, and this is actually one of the things we really want to do. For instance, I could get the idea that I want something like the exponential of IA, say. You know, exponential IHT is the time evolution operator we remember from the axioms. But what is this supposed to mean if A is unbounded? Well, the answer is it's supposed to mean a function on something like, let's say, any unbounded operator. It doesn't need to be so it's actually supposed to be the integral dp if the A, if this is the P that belongs to the A. So if I take the AP here, for instance, at our level of understanding, I will simply take the function of the values over here, and now it's more. So I can actually write this x. Okay, I take simply x as a function times dp. Times, what x will e to lambda and produces e to the lambda. So this is as much as x takes a real number and produces a complex number by sending lambda to e to the lambda. So that's the x function that I'm using here. So we've taken x of the operator and integrated with the measure that belongs to the operator, but not over the identity, but over exactly the function we want to evaluate. You could never do this for unbounded operators by the series. You know, you've probably been instructed somewhere if you have e to the matrix, you just write down the series, right? And then you have a matrix to the power of, the exponential series. Why can't you do this for unbounded operators? Well, it's a series. It goes to infinity. So you need to use the norm to check convergence. It would be the operator norm. But on the unbounded operators, you have no operator norm. The operator norm only exists on the bounded operators. That means if you have an unbounded operator and you want to define e by the series of e by the exponential series, you wouldn't even know what the series means, what the convergence means. And that is not an option. Hence, you have to do it this way, and this would be well defined. So that's one of the applications of the spectral theorem. More, including the proof of the spectral theorem, will follow next time. Thank you. final lecture of the series, and today I would like to point out where the subject is taken, or was actually taken 100 years ago, because when quantum mechanics proper was born, by Schrödinger and Dirac and Heisenberg and so on, there was already, the first revolution in physics of that century already had taken place in the relativity. And so what we will do today, we'll look at quantum mechanics in a relativistic context. And that is a huge subject, but in fact, it could be that only small modifications to the existing formalism and equations would be necessary. To add an extra term, that extra term takes care of the relativistic effects. Well, nothing could be further from the truth. Relativistic quantum mechanics, it turns out, will be crucially different from non-relativistic quantum mechanics, and today we'll discover also in a technical sense why. And if we follow that route, we first come to the Klein-Gordon equation, then the Dirac equation, and so on. That's all peanuts. But then one realizes that these equations, so if you make the Schrödinger equation relativistic, this equation is no longer has a probability interpretation. So one thing is the dynamical equation that carries the solution or the state forward, and but the other thing is you must be able to interpret that physically, and that miserably fails. And in the beginning this was quite a puzzle, but of course we can pinpoint exactly where it fails and why it must fail. And there is no relativistic quantum mechanics in the type of the Schrödinger equation, even with modifications. The so-called Klein-Gordon equation and Dirac equation, they are not solid quantum mechanical equations. One is forced to go to quantum field theory. So this is where the whole subject is going. Now, let's, however, review a little. So let's say start first with heuristic deviation of the Schrödinger equation. So we go back to something we actually cast into an axiom. Remember, axiom 4 was essentially the Schrödinger equation expressed in terms of the state, rho. Now, it's easy to write down an axiom, but the question is how do you get there? And the thinking goes as follows. So Schrödinger recognized, now one can think about what is true, but we're not going into that. Schrödinger recognized that replacing the energy, wherever it appears, by plus I h bar by dt, sorry, I should say replaced by, and replacing the momentum in the nth direction, so say in a three-dimensional space, a is 1, 2, 3, replacing this by minus I h bar in the direction of the eighth component. This is the t component of a wave function family. That replacing e by that and by that where? In the energy-momentum relation. Well, the energy-momentum relation of non-relativistic mechanics. And what is that? Well, you know, this is the total energy E is the kinetic energy, so that's P squared divided by 2m plus the potential energy. And making thereby a differential equation or differential operator, you need the Schrödinger equation. So you do that on the left-hand side, you get I h bar e by dt, well, it needs to act on something, you write a psi. And right-hand side, you replace the p, that gives a minus bar squared 2m, and then you have the Laplace here, psi plus v of x acting on psi. And you know this is the Schrödinger equation. And we talked about these Schrödinger operators and so on. So that is how you can motivate this. Of course, you have to think about this here. Well, this here, the p's go to this, and the q's are multiplication. That's the same for Neumann theorem. And well, this is the extension, so you get the Schrödinger equation. Now, for whatever reason he did that, now assume somebody suggests this equation and says, well, I want complex representations of that. Something like this, okay? How would you interpret this? And of course, you can invoke another axiom, our axiom 5, and say, well, the interpretation is fixed to be such that this is a different rho, this is not our state rho, this is a probability density rho. You just take the absolute value squared of the field, you then get a real field, so the result would be something from R3 to R, and notably to R0 plus, because the absolute value squared at every point x is of course a non-negative real number. And you say, I interpret this as a probability density. In this case, for a particle to be at the point x. Well, that makes not much sense. You have to make little intervals over little regions, and then you get a finite probability. There's only probability density. Well, one can say something like this, but the question is, how on earth do you get the idea? How on earth? And so when this equation is there, so question, how does one get this idea to interpret rho as such? Well, if you want to interpret it as a probability density, you actually need two things. First of all, you must know that it's never less than 0. That's for sure. Well, this would be true by construction, but so there's nothing else to be said. But there's another problem. If you integrate this rho over all of R3, it better be 1. So, okay, I can always arrange for that. Yes. But it's kind of a static thing. Now imagine you let the time run. You investigate how this changes if you look at this at different points in time. Then this integral better do not change. You better keep 1, because otherwise you lose probability. That makes not much sense. Right? So the axiom can be there as it is, but you need to ensure this, or it needs to be ensured already, otherwise the axiom is a nice axiom, but it makes 0 sense. So what do you study? Well, you take the equation as it stands, and you investigate its properties, and it takes 2 lines to see that everything is well. So let's do that. And the reason why I do that is because in a second we'll go to the relativistic version of it, and we'll see nothing is will, and nothing can be repaired. Not in a conservative sense. So obviously, without the time evolution of that equation, you have to study this equation because the left-hand side is the change in the psi, the right-hand side doesn't depend on the change in t. So what we do, we consider the Schrödinger equation and its complex conjugate. So we write down I h bar d by dt psi equals minus h bar squared by 2 Laplace plus b, well, we let it act on the psi. And I consider at the same time complex conjugate. Well, there is no extra information in it. It's the same equation. Put a bar here, minus h bar squared by 2m Laplace psi bar. The bar, of course, goes in plus v psi bar. It's twice the same equation. Now, what I do on the right-hand side of the first one, I multiply by the complex conjugate of the field. So